All right, so let's clean up a few things from the last lecture before going into lecture 3. So fragmentation and reassembly. So what is this? Well, basically, if I'm layer n, I get some payloads from above. Okay, and then I use the layer below me to transmit these payloads. Now, for technical reasons and other reasons, it might be that the layer below me is unable to has a maximum size of the payloads it can accept. So maybe there are 500 bytes maximum that the layer below us can transmit. Now, what do I do when I get 1,000 bytes from above? Well, I split it into two parts, transmit each part separately. At the receiving end, I get two parts up from the layer below. I glue them together before delivering it up to the next layer. So this is called fragmentation and reassembly. And this is done transparently to the layer above it. Okay. So this is a way of providing a better service to the layer above because there is a less of a limit on the payload size, right? Even though that the layer below us is limited in this sense. There's the opposite somewhat is not really the opposite, but aggregation and deaggregation has to do with efficiency. So it might be that the layer below us needs a certain number of bytes to do its job. There is a minimum size of the payload that we can push down. It could also be that we know that for each payload that I push down the stack, there is some overhead in terms of headers for that needs to somehow be transferred also. And if it's for efficiency reasons, it could be good to take several payloads from above, glue them together into one single payload before feeding it down to the layer below us. Okay, and this is done for efficiency reasons, for instance. Then on the other side, I get up from the layer below a packet which has several service data units in it. So I put them aside and push them up individually to the layer above it. Okay, so again, this is transparent to the layer above it, above us. So this is called aggregation and deaggregation. Multiplexing is a very important thing. And if I'm a protocol in layer n, there might be several protocol entities above me that would like to use my service. Okay, so I can service several customers, if you like, from the layer above me. So if I'm IP, for instance, I can service DNS, I can service HTTP, I can service a bunch of other protocols that can be running simultaneously from above. Okay, so if we have this that we have maybe here HTTP and here okay, so there is something missing here, and here maybe we have DNS, right? So there could be two different protocols on the layer above it, but regardless, they are transmitting data in each of them using a service access point. But when it goes into one particular entity here, just a single entity here, which transmits the blue payload and the purple payload over the same logical connection, but at the receiving end, these are then fed up into the appropriate service access points. So whatever message goes from this entity to this entity, namely this one, is then transmitted over a logical connection, the same logical connection as this payload, the purple one, but at the receiving end, these are then demultiplexed and sent up into the appropriate service access point. Okay. And to do that, we need some identifier in the header to explain to which service access point the blue one should go. So the blue one goes down here, goes over here, the multiplexing tag is inspected here, and then this entity knows that it should send it up here. Okay. So, for instance, these multiplexing tags here could be port numbers. Okay. If this one happens to be the application layer, and this is then the transport layer. Okay. Splitting is the inverse multiplexing, and here it's oops. Sorry about that. A layer n plus one entity may use multiple services, multiple layer n services. So an entity here which needs to transmit service data, needs to establish this logical connection with the blue payload and the purple payload. When this is pushed down, it can be pushed down to two different protocols that do this. So. And this is done maybe to get higher data rates, because maybe the data rate over this link is limited to something, say 1 megabit per second, and maybe this is limited to 1 megabit per second, but then this one can get 2 megabits per second by using two parallel paths like this. Okay, so this is called splitting inverse multiplexing. All right. And then to finish this off, if we look then at the OSI reference model in more detail, we have, as we learned from before, 7 layers, 1 to 7, and typically these 3 layers are then merged. Okay, but in the full model, we have 7 layers. The top layers here, application, presentation, session, and transport. Whatever entities are run in these layers are communicating with entities at this node, and it's on the other side of the network. So from end to end, these protocols talk to each other. So the transport layer, the TCP, for instance, here in this node, the host here, talks to the TCP here. It doesn't talk to any of the TCP. There is no TCP in between. There are no TCP entities in between. There is a TCP running here. There's a TCP running here. Nothing in the routers. Okay. The routers, however, are running network layer stuff. Okay. So network entities here talks to the network entity at the intermediate nodes. Possibly not all of the intermediate nodes, but at some. The data link layer talks definitely with the data link layer entity on the other side of the link, and the physical definitely does this, right, over this cable. So we'll see more about this later on. The main point I would like to say is that the top layers here are end-to-end protocols, while the lower layers here are more over one hop each. Now, the network layer here can indirectly talk to the network layer here, but it does that through the other network layers. Okay. So there could be some information flow that goes from here to here, but it goes, it is processed along the way. Okay, while the transport layers are not. Okay, we'll skip this. And then I'll let you read through this. So it's a little bit basically a repetition of what I said earlier. So I'll skip that in the interest of getting to the more important things to prioritize the lecture 3 things. Okay, so that about lecture 2. And let's go to lecture 3. So here we will start to continue to talk about protocols, and we now go from this more abstract or say theoretical model, the OSI model, to the TCP IP model, which is used quite much in practice. So terminology in networks, there are nodes, hosts and routers. Hosts run end user software. Routers relays information inside the network. A link is a physical medium that connects nodes. We have an application that uses the network. So we talked about that. We talked about layers and protocols. So a layer is something, a set of connected communication functions that provide the service up by using the services below. We have connection-oriented or connection-less services. Blah, blah, blah. I think maybe we can skip this since we talked about that just half an hour ago. So to save this. So this is the repetitions. Okay, so this is new. Or this is also repetition. So let's go into the OSI model and then talk about the internet reference model. Okay. So here, first of all, there is no exact translation of the layers between OSI and the internet model. As a matter of fact, one might challenge that the internet model is not completely obeying to all the rules which are set up in the OSI model, separation on networks and things like this. And as a matter of fact, if you Google this, you sometimes see that the internet model has 4 layers or 5 layers. Okay, so it's not even clear how to draw the lines between layers in the internet model. So the original model, I would say that when this was created in the 60s as a research project, then one talked about 4 layers. Okay, we had the application layer, transport, internet, and the network interface layers. And a translation from the OSI model to the original internet model is like the lower 2 layers plus parts of layer 3 was in the network interface layer. And some functions in network 3 in the network layer in the OSI model was in the internet model, and so forth. The internet model, which is used in the book and sometimes is maybe a little bit more modern way to do this, I don't know if we can really exactly claim that, but we will talk about the OSI model, the internet model in this course as consisting of 5 layers: application, transport, network, data link, and physical. And as you see, it has basically the same names as in the OSI model, right? But not the same name as the original internet model. So when you Google, you might get information that pertains to these layers, which are not directly mappable, which is a little bit different from these layers. Yeah. It's just part of the messiness of the TCP/IP model. TCP/IP model. Okay, so the internet model is also known as the TCP/IP model. So then the question is, we talked about this in a little bit, that we have these, protocols and so forth. But who actually decides about this? Is it the government, right? Is there laws about this? Who decides about this? But the answer to this is actually there are different standardization bodies. And so why do we need standards? And standards we need in order to make sure that equipment from different manufacturers can still work together. So this notion about interoperability is super important when it comes to standards. And if we have interoperability, that is that you can buy devices from many different manufacturers and you are pretty sure that they can communicate with each other, we also create a good market, right? Because you as a customer, you can choose to buy stuff from here or here, right? Because they do the same thing. You can compare prices and so forth. And also the people that do, for instance, chipsets for this can make the same chipset and sell it to different vendors. So you create a mass market. Super important. So different protocols and so forth are defined by different standardization bodies. We have ITU is a body which is actually a part of the United Nations, believe it or not. They deal with telecom, so this is a pretty old thing. A couple of beginning of 1900s, late 1800s when this was created, when radio started to become popular. Nowadays they do many different things. These are a few of the standards that they are responsible for. IEEE takes a large part of this. They develop Ethernet, Wi-Fi, other things. The Internet Engineering Task Force deals with how things are supposed to be run on the Internet. So maybe these are the lower layers and these are the upper layers. Okay. So they specify HTTP, for instance, DNS, how that should work, and so forth. Then there is something called the W3C, which specify web standards, so HTML and different things you need in order to build a website. And then 3GPP deals with mobile wireless networks, for instance, GSM, 3G, LTE, 5G, and so forth, right? And all of these lives in sometimes a collaborative climate and sometimes a little bit of a competitive one. Standards is a tricky thing because there's a lot of commercial, political, and other issues that goes into this. So a technology which is standardized is not always the most technically efficient one. But that's an unfortunate fact of life. Okay. So if we continue and talk about internetworking, so this is a little bit of a complex slide, but if we look here on the left-hand side here, suppose we have Alice here on the top. So Alice is running some software on her computer, and she would like to contact Bob, who's running some type of maybe web server or whatever, but she needs to talk to Bob here. Okay. So Bob is connected to a local area network, and so is Alice. But they are disjoint before they attach to the internet. And the internet is consisting of, in this case, several networks. We have a wide area network here, we have a router here, another wide area network to this router. Here we have a wide area network to this router. There's another wide area network to this router, and then there's this router is connected to this local area network here. So it's kind of a complicated thing here. And in each of the routers here, we have a protocol stack. So let's draw this a little bit. Okay, so we have Alice. At Alice's computer, there is a protocol stack. Okay, and it consists of the application, transport, network, data link, and physical layers. Okay, so it's a complete stack. Same thing at Bob's place. We have application, transport, network, data link, and physical. Okay, and if we remember from the last lecture, the application and transport layers, these are end-to-end protocols, which means that the application layer at Alice talks to the application layer at Bob. But we see in the intermediate routers here, there is no application layer, right? It's not a complete stack in the routers. The routers only have physical, data link, and network layers. And the reason for this is that there is no application software running on the routers. Hence, there is no need for an application layer here because there is no application software to run, so there is no need for an application layer. For reasons which is not super clear here, but there is no need for a transport layer either. It's enough with the network layer for it to do its thing here. Okay, now, so data needs to be transmitted from Alice to Bob. So how is this done? Well, it's done like this. The data goes down the stack at Alice to reach the physical layer, and then goes over to the router 2, where it's received by its physical layer, goes up the stack at the router to the network layer that figures out where the data should be transmitted next time. Goes down the protocol stack at the router, down to the physical layer, which connects R2 with R4. It goes into R4, goes up the protocol stack here, figure out the next hop, goes down the the protocol stack, and then is routed towards router number 5, goes up there, down, up in 7, down in 7, reaches Bob, and then goes all the way up to the application layer and the application layer software. So this is the physical path of the information. Logically, the application layer at Alice thinks that it talks to the application layer at Bob and has no idea what's going on in the middle. That's the beauty of the layering, right? We hide the complexity of the network to the layers above us. Okay. Another way to illustrate this is to have problems here. To think of Alice on the top here and Bob on top of this. And a more abstract view of this is basically that we have a network that connects Alice with the router number 2. We have a network that connects router number 2 with router number 4, and so forth. So we have these intermediate networks, and data is then supposed to flow through these networks. Okay. And this is why it's called internetworking, because the data goes through several separate networks, all of them interconnected with routers. So here's an example of an internet. Okay. So internetworking is needed to provide connectivity between hosts that are attached to different networks. So Bob is attached to a local area network here. Alice is attached to a local area network here. Okay, so then we need internetworking because they are not the same network. If Alice wants to talk to Bob, messages needs to traverse 5 networks, 1, 2, 3, 4, 5, before it reaches Bob, right? And these networks are then connected with routers. Now, you might want to argue, so what about this switch here and about these switches here? As we will see later on, these switches are often run in transparent mode, so they're not visible to the network layer which is on top of them, or the data link which is on top of them. So they're not counted here. I know it's hard to understand why this is the case right now, but let's just accept it for a fact that switches are not part of, does not separate networks. They're part of one network. Okay, so we will see how that works later on. So in the TCP/IP model, it's the protocol IP that provides this functionality. That is the functionality to transmit data over several networks. Okay, so let's talk about the TCP/IP protocol suite. So we have 5 layers, the data link layer and the physical layer. And sometimes these are bunched together. And on the bottom here, we have a bunch of different communication technologies, ADSL, LTE, Wi-Fi, Ethernet, you name it, right? There are multiple ones here. Okay. On top, we have the application layer protocols, and we already talked about HTTP and DNS. SMTP is the protocol that governs emails. DHCP is a dynamic host control protocol. We will see what that does later on. But there is a number of protocols here. In the transport layers, there are 3 main protocols: TCP and UDP and SCP. Okay, we'll talk about that on the next slide. In the network layer, there is only one main protocol, and that's IP. And then there is a couple of helper protocols here, and we will talk about a few of those in a minute also. But the thing is that it's basically just one protocol in the network layer. There are 3 in the transport layer, and there are many, countless numbers on the application layer. And there are almost countless numbers of different communication technologies in the data link and physical layers here. And actually the key to success here is that IP, everything goes through IP. Okay, so it's like the main thing that everything goes through. And actually that turns out to be a very successful thing. So HTTP goes over TCP, which goes over IP, and maybe that goes over Wi-Fi. I don't know. DNS goes over UDP, which goes over IP, which maybe goes over 4G. I don't know, right? But the different things is that everything goes through IP here. That provides this connectivity between different networks. And yeah. Okay, so IP hides basically the mess that's below here and provides a unified service up here. to these protocols here, which refines them for different purposes of the application layers. Okay, so let's talk about the middle layers here, the network layer and the transport layer. So what is the service provided by IP? It is best effort, connectionless, packet transfer. Okay, so what does that mean? Packet transfer basically means that it can accept a block of bits and transmit those. Okay, so that's not a big deal. Connectionless means that it does not establish a connection to the other side before actually transmitting data. So if I'm the IP layer, I get some data from above, I put that in a packet, and I just push it down into the network without any further ado. Okay, so it's connectionless. Best effort, what does that mean? It means that, okay, I'm trying to do my best, but I guarantee nothing. So the data I get from above, you know, maybe it arrives, maybe it doesn't. I don't know. I cannot promise the layer above me, whatever you give me, I will make sure that it reaches the other end. It makes an effort to do this, but no promises. So it's not a reliable protocol. Okay. Now, the transport layer, we have three main protocols. So the first one is UDP. And UDP is nothing but a fancy wrapper around IP. So it basically does nothing that IP does not already provide. So it's not much of a refinement of the service at all. So it provides what's known as a datagram service, which is same as packet service. It's just a block of bits that it can transmit. It does it in a connectionless manner, and it does it in best effort. So it's just a wrapper around IP. And maybe this is good enough for some of the application layer protocol, right? There might be some application layer protocols which is completely happy with this type of service, and therefore basically everything goes pretty fast over this interface because there is not much UDP needs to do, right? So it's a fast, economical protocol to provide a service which is best effort, connectionless, and basically transmit packets. Okay, but some protocols would like to have better things. So there is where TCP comes in to play here. So TCP takes the service of IP, best effort, connectionless, and packet transfer, and does what? First of all, it provides reliability, number one thing, which means it guarantees any information that comes from above will arrive at the other end. You know, barring a nuclear catastrophe or something like that, right? But for sure, it will provide a reliable service. It does that also by providing, it's a connection-oriented service. So you basically set up the connection before you can transmit data. It provides full duplex communications, and it provides a stream service. A stream service is basically that it can take a stream of packets from above and provide that stream at the other end in order, error-free. Okay. Question?
What does best effort mean?
Best effort means that basically no guarantees. Okay, so you're not, if I'm IP and I get a packet, I will do my best to transfer that, but I don't guarantee anything. It can be lost. Right? So basically what TCP needs to do then is to take this unreliable service and provide functionality to make it reliable. And we will see how one can do that later on in the course. So this is a much more refined service, and sometimes this is what the overall, the protocol above it would like to see. Okay, these are the two main protocols, UDP and TCP. Now there is another protocol here also, which is not so well known, and it's not so prevalent. It's not used so much, but it has some very nice features. Basically, the difference between TCP/IP and TCP and SCP here is what's in red here. So it provides still a reliable, connection-oriented, full duplex stream service, but it also provides multi-streams, which means that you can have several streams from the layer above, and you can manage those. So you can have several streams from above. It also, which is not clear why that is a good thing, but it allows for this what's called multi-homing, which is not so understandable at this moment, but basically means that it provides communication over multiple IP addresses at the same time. We'll see a little bit later what that actually perhaps means. Okay. But again, I think the most important thing here in this slide is to understand that there are several protocols in the transport layer, but there is only one protocol in the network layer. The network layer is not very reliable, right? And sometimes you're okay with this, then you use UDP. It's fast, it's cheap, economical. If it's not enough, you use TCP, which is slower but more reliable, full duplex. Also have a stream service, so you can. There is some idea that packets that comes down from the layer above them has some ordering implied in them, and then TCP will make sure that it's delivered in order and also reliable. And then if you want even better service than TCP can provide, you can go with SCP. Questions? Okay, so let's continue then. For things to work, we need addresses. And we already touched on this. We have talked about these internet names and internet addresses. We already touched on that earlier. So if you remember, internet names are unique and easy to remember for humans. It's something which is independent of the physical location of the entity that we talk about. And the host names have I should say internet names here. I had two parts. So here we have an internet name, right? It has a host part and a domain part. Okay, so yeah, that's what it has. An internet address is something that uniquely identifies a network interface card. Okay, a network interface card might have several IP addresses. A node can have several IP addresses if it's attached to several networks. And routing decisions are based on these IP addresses. IP addresses have two parts, just as internet has two parts. It has a network identifier and a host identifier, and where the boundary between these goes is variable. Okay? Internet addresses are 32-bit strings in IPv4 version 4. It's a larger space for IP version 6. So it's also in this decimal dotted notation. So this corresponds to 8 bits. So this is a number from 0 to 255. So it's 8 bits here. This is a number between 0 and 255. So 8 bits, 8 bits, 8 bits, 8 bits. 8 times 4 is 32 bits. One of the problems with IPv4 is that there are too few of these addresses for the internet as we have it now. So IPv6 is much larger address space. Okay, so we have in a computer a network interface card, say. Okay, and if we have an IP address, it will point to this network card. There might be another IP address number 2, that also points to this network interface card. Okay. But an IP address will never point to two different network interface cards. Okay. It's from IP to network interface card. That's a unique mapping. Okay. A network interface card might have several IP addresses. Okay. a host like this has an internet name and it's associated with one IP like this, and that is translated through DNS. Okay. Let's continue. Then we have link layer addresses, and local area networks assign link layer addresses, also known as physical address or MAC addresses, to what's known as the physical attachments to the network, which is a fancy name for the network interface card. Okay, so the network interface card has a link layer address also. The link layer address is unique for that interface card. And okay, so we have here a MAC address or physical address or a link layer address. These are the same things, right? So when this network interface card is manufactured, it gets a link layer address that it keeps for all eternity, in theory. In practice, it can be reprogrammed. But for simplicity, we think of it as being fixed. The IP addresses is assigned dynamically to this network interface card, depending on where this computer is actually today located and on power up. So when I take my laptop, I power it up, my network interface card link addresses is the same if I power it up here or at home. But if I'm here or at home, I will get different IP addresses. Okay? So the IP addresses are dynamic. And these are fixed. Another way to think about this is that your MAC address is like your personal number. It's something that you get not on production, but on delivery, right? And then you keep that for your whole life, but your IP is where you live. Okay, so you might move to different places and then you have different addresses. Okay, and we know that both the personal number and your address are useful, but maybe in different contexts. Okay, so one example of a link layer address or a link technology is Ethernet, and it uses 48-bit addresses. So each Ethernet network interface card has a unique global medium access address, MAC address, which is also the physical address, which is also the link layer address. The first 24 bits identify the manufacturer, and the second 24 bits is some type of serial number. So in my laptop, for instance, I have a network interface card with this address. So colon here separates, so we have two hex numbers. So a hexadecimal number is 4 bits, 0 to 15 or 0 to F. So here's 4 bits, 8 bits. So 8, 8, 8, 8, 8, 8. 8 times 6 is 48 bits. First bits here tells me that Apple did this network interface card. Okay. Now, if we want to translate between internet names and IP, we use DNS. How we translate between IP addresses and MAC addresses here, we use a protocol called ARP, Address Resolution Protocol. Okay. We'll talk shortly about how that works. Okay, so talking more about link layer addresses, there are actually 3 main types. There is unicast, multicast, and broadcast. addresses. So what I talked about here, when a MAC address identifies a network interface card, it's something that it gets, a personal number it gets when it's manufactured. That's a unicast address. It addresses a single node on the network. However, for things to work from a protocol point of view, we would also like to have logical, this is a misnomer, but logical physical addresses. Okay? These are physical addresses in a physical address format that can address more than one single node. So we have multicast nodes, multicast addresses, which is for point-to-multipoint communication. And we will see a little bit later why this is useful. And we also have broadcast addresses, which is point-to-multipoint addresses, which addresses all nodes on the network. So multicast addresses more than one node, but potentially not everyone, while a broadcast addresses all the nodes on the network. Okay. So internet, for Ethernet, we have unicast, multicast, and broadcast. And a unicast is an example of something like this. And a multicast looks something like this. The broadcast looks like this. Okay, so there is only one broadcast address, and it's the all one address. So F is 111, right? So whenever a frame is transmitted with this address, every node on the network will pick this up and process that information. When we use a multicast, those who belong to that multicast group will pick this up. If it's unicast, only one network interface card will process that information, namely that one which is addressed. Okay, and for Ethernet, this is not super important, but the second digit here needs to be even for unicast and odd for multicast. And this is actually a typo in the book. That's why I put it up here. That's nothing I will ask on the exam, but that's how you can distinguish between them if you happen to be a network interface card. Okay. How to obtain and resolve these addresses. So the internet, we had a question about this. How do we know this address? How do you get that? Well, basically you purchase a domain, right? So if you're Chalmers, you pay for having the domain chalmers.sc. So companies and organizations, they pay for this, and they pay that by going to a special company called the domain name registrar, all right? So man rent the domain name from this registrar, so man pay an annual fee for this. The biggest such register has this funny, I don't know if you had heard of the company GoDaddy. Yeah, but that's an internet registrar. It happens to be the largest in the world. So basically I go to GoDaddy and I pay a fee for this, and then different types of domain names have different prices attached to these. Some people made a lot of money at the early stage to register, for instance, food.com or pizza.com and things like that, and that turns out to be quite valuable at the end, right? And some people actually registered apple.sc. It was not apple.sc, but take a famous company, Coca-Cola, whatever, and then bought some of these domain names. That's not okay, so they were actually not being able to blackmail the companies for large amounts of money. They would just, so you can't register whatever you like, right? That's what I'm trying to say. But some people registered, for instance, these TV domains and things like that, and made some money out of that. Okay, so this is not important for the course. So let's continue. So how do you get IP addresses then? IP addresses you get dynamically. When you power up your laptop or your phone, it searches for a network, and when it finds the network, on that network it searches for a DCHP server, dynamic host configuration server that gives you an IP address, right? So if this happens to be a router, which is not, but if it would be a router, if I plug this in and I power up my laptop, there is a server here that assigns an IP address to whatever was powered up. Okay. So you get your IP address as a power-up, or you can also manually configure those. Link layer addresses, you get that at manufacturing. Okay. So domain name registrar gives you the internet name, and it's also something which is dynamic. I mean, it can change from time to time. It can move around to different computers, and then you have to enter into the DNS database what the local IP and domain internet name matching is when you do that. Okay, and then we have IP addresses, which is manually configured or use DHCP. And then you have the link layer addresses, which you get at manufacturing. If you want to translate the internet name to IP, you use DNS. If you want to translate an IP address to a link layer address, you use ARP. Questions so far? No? Shall we take a break then? 15 minutes?